Ever pondered if there's a difference in brain activation between deaf and hearing native signers? Today, we're diving into the fascinating world of neuroscience to explore just that. We'll be looking at how the neural systems recruited for language processing by native signers might differ based on their hearing status. We'll journey through a series of intriguing studies that have compared brain activation patterns among deaf and hearing native signers. Stay tuned as we delve into various intriguing studies that have explored this very question. Numerous studies have contrasted hearing children of deaf signers with deaf children of deaf signers in terms of brain activation. Researchers like McSweeney and colleagues have delved into this intriguing realm of neuroscience. Their findings? Certain differences in brain activation between these two groups do exist. One of the key differences lies in the auditory processing regions within the temporal lobe. For hearing people, these regions tend to be less active when processing signed language or sign-like nonsense gestures compared to deaf native signers. It seems that even when a visual language is learned first, auditory processing tends to dominate in these cortical regions. But what happens when there's no auditory input, as is the case with deaf individuals? Well, these regions don't just sit idle. Instead, they can be recruited to process input from other modalities. This brings us to an amazing concept known as cross-modal plasticity. It's the idea that certain brain regions, typically led by one sensory process, can adapt to serve other sensory processes when circumstances and experiences dictate. Fascinating, isn't it? But it doesn't stop there. Bavelier and Neville, among others, have found that being deaf from birth and early exposure to sign language can have distinct impacts on brain function. An interesting study by Bosworth and Dobkins found that people with early exposure to sign language, regardless of their hearing status, showed more efficient processing of simple dot movement displays in the left hemisphere than the right, a clear divergence from hearing non-signers. And here's another intriguing twist. In deaf individuals, watching moving dot patterns can actually activate regions that typically support hearing in hearing people, as if the unused auditory cortex is being colonized by vision. Greater activation in this region has also been observed in deaf signers when watching British Sign Language and nonsense gestures. So it seems that exposure to signed language and congenital deafness can potentially reroute the tracks of brain development. Different patterns of brain function may emerge that are more efficient for the individual's specific environment or circumstances. These findings point towards a fascinating aspect of our brain's adaptability. But what happens when we move away from language and look at non-linguistic processing in hearing signers? Well, let's dive into the research of Bosworth and Dobkins. They discovered that the processing of simple dot movement displays was more efficient in the left hemisphere than in the right, in those exposed to sign language early in life, whether they were deaf or hearing. This was a departure from what was observed in hearing non-signers. Now let's shift our focus to the work of Bavelier and her team. They used functional MRI studies to show that visual attention to peripheral events was more efficient in deaf people compared to hearing individuals, even though both groups were signers. This suggests that the necessity to pay attention to peripheral visual events, a functional outcome of hearing loss, drives the deaf brain to reconfigure itself. A different form of functional plasticity was observed in relation to auditory processing regions. Finney, Boynton, and Dobkins found that in deaf, but not hearing signers, the movement of visible dot patterns caused activation in regions that typically support hearing in hearing people. This indicates that unused auditory cortex can be colonized by vision. These studies underscore the profound impact of our experiences and circumstances on brain function. They show us that both exposure to signed language and congenital deafness can reset the course of brain development, leading to different, more efficient brain function patterns for the specific environment or circumstances of the individual. We've covered quite a lot of ground, haven't we? We've explored the intriguing world of brain activation in deaf and hearing native signers. We've seen how similar the brain localization patterns for deaf native signers processing signed language are to those for spoken language processing in hearing native speakers. But we've also unearthed that hearing status does influence the neural systems recruited for language processing. Particularly, auditory processing regions in the temporal lobe are less active for signed language in hearing signers compared to deaf signers. We've also delved into non-linguistic processing. We've learned that early exposure to signed language, regardless of hearing status, influences brain function. And we've seen how the deaf brain reconfigures to better attend to peripheral visual events, a consequence of hearing loss. As we've seen, both signed language exposure and congenital deafness can steer brain development in unique directions, leading to different yet efficient brain function patterns. Isn't the human brain truly fascinating?